Hello everyone, my name is Keiichi Chai from NTT Docomo, which is one of the largest mobile operators in Japan. The paper I will be presenting today is titled Disaster Damage Estimation from Real-Time Population Dynamics using Graph Convolutional Network. Firstly, I'd like to describe the motivation of this study. Weather-related disasters such as typhoons and heavy rains due to climate change are occurring more frequently. The Tokyo area experienced 2 strong typhoons in 2019. Typhoon Hagibis caused 47 rivers breach their bank because of heavy rains. In such situations, a speedy and accurate response to the disaster is crucial for national and municipal governments. However, as the damage scale becomes larger, it takes more time to grasp the whole situation. Therefore, it is important and necessary to estimate the severity of damage at an early stage. Here, we give an example from the case of Typhoon Faxai. The typhoon made landfall over Chiba Prefecture located east of Tokyo. From the data published 1 week later, we can see that the Chiba Prefecture had a slightly severe damage or more than other prefectures, as indicated by the dashed red line. However, the data from a month later, represented by the red line in the figure, reveal that Chiba Prefecture suffered even more serious damage. This example illustrates the difficulty of grasping the whole disaster damage situation immediately after a disaster. So our goal of this study is to estimate the severity of damage at an early stage. Estimating the severity of damage at an early stage after disaster is a challenging problem. There are several possible approaches, such as using satellite imagery, social media, and GPS data of mobile phone. Unfortunately, there are limitations to these approaches like these, such as limited temporal resolution and geographical coverage, especially for rural areas. In this study, we focus on real-time population data generated from cellular networks. Cellular network-based population data is suitable for this task because it has high reliability, high temporal resolution, and a wide range of coverage. We propose an approach to estimate the severity of disaster damage within a short time period after a disaster occurs by exploiting real-time population data generated from cellular networks. There are 2 hypotheses of this study. The first one is we assume that population dynamics of a city depends on the severity of damage. For example, we expected that the presence of residential population in a city will increase and non-residential population will decrease after a natural disaster over that of normal time. So we design effective features based on population dynamics after typhoon passed. The second hypothesis is population dynamics is affected by intercity population flow. Based on this hypothesis, because graph structure of cities is effective for estimation, we design graph convolution networks for disaster damage estimation called D2DCN. From here, we describe the details of our study. First, we explain cellular network-based population data using this study called Mobile Spatial Statistics, MSS. The MSS data is estimated population data based on NTT Docomo's cellular network. Real-time version of MSS data is calculated at 10 minutes intervals for each of the 500-meter grid squares to provide up to 1 hour before of the current time. The MSS data only provides aggregated population, not the trajectory individuals to protect user privacy. An example of MSS data is shown in this figure. The details is described in the last year's Spatial paper by Agaska et al. Here, we provide the problem formulation. Given the real-time population history XC of a city C, our goal is to estimate the disaster damage level YC. YC is labeled by a disaster recovery law, which is applied or not, published by government. So we formulate the disaster damage level estimation problem as supervised classification problem. Before we design estimation model, we conduct an empirical analysis to obtain insights. Our hypothesis is population dynamics of a city depends on the severity of damage. More specifically, the presence of residential population in a city will increase after natural disaster over that normal time. Conversely, the presence of non-residential population will decrease in comparison to that of normal time. So we investigate the population ratio against the normal time and compare the population ratio among less damaged cities and serious damaged cities. Population ratio of less damaged city recovered to normal ratio immediately after typhoon passed, while that of serious damaged city is significantly changed. This slide shows the overview of the proposed method. Based on the empirical analysis described in the previous slide, we designed 3 types of features regarding population ratio using city-wide data. On the other hand, we construct a directed city graph. Nodes of the graph represent cities, and an edge is added between 2 nodes if there is an interstate population flow. The weight of the edge denotes the number of people who moved between the 2 cities. These features and a directed city graph are inputs to our GCN model that is edge-weighted GCN to estimate the disaster damage level for each city. We extend basic GCN for directed and weighted graph. We propose the following neighbor node aggregation function to consider the directional information and edge weight. We evaluated our method using 2 typhoons hit Tokyo in 2019. Total number of target cities was 171. The level ratio were almost 30% for level 1, severe, and 70% for level 0, non-severe. We compare our DCN model with model which does not consider graph structure of cities. For example, XGBoost and RightGBM. And we also compare the existing DCN models with basic DCN and graph stage. The comparison result is shown in this table. Our DCN model was the best performance. Next, we evaluate the effect of graph characteristics of the directed city graph. Specifically, the unique characteristics of our directed city graph compared to those of the existing studies are directed and weighted edge. So to analyze the effects of each component, we perform the ablation study. The combination of directed, undirected, and weighted, unweighted were compared. This graph shows the results. From this graph, we can see both direction and weight information is effective for estimation. Apart from the quantitative evaluation of classification performance, we also conducted a qualitative evaluation to analyze the effectiveness of features. This table shows the feature importance of RightGBM model. From this table, we found 3 insights. First, anomaly score is more effective than population ratio. Second, total population is more effective than other population. Last, nighttime population is more important. In the case of Typhoon Faxai, large-scale power outage occurs in Chiba Prefecture, so we need to consider the effect of blackout. However, although we need more examples of disaster to conclude the effect of blackout, the information on the occurrence of blackout itself may be useful for estimating the disaster damage level. Our empirical results reveal that the proposed method can achieve a certain level of estimation accuracy in the case of Typhoon, Fox, and Hagibis, there are several limitations. We need to validate the generalizability of the proposed method by using other disaster data. Second, the estimation performance has room for improvement. First, we would like to extend our model to estimate the disaster damage level of a fine-grained location, such as grit level or a fine-grained severity level, for example, multi-class and regulation. We summarize the lessons learned in this study. First, because the graph structure effectively captures the population flow, GCN model can improve the estimation performance compared to a method that does not consider the graph structure of cities. Second, because the population flow has the direction and the amount, not binary information. The model that leverages this information is valuable for analyzing the population flows. As a result, the proposed method outperformed the baseline method regarding all metrics by up to 10%. This study revealed the potential of rescuing more people in a disaster situation by estimating the severity from population dynamics. Conclusion. We propose an approach to estimate the disaster damage level by exploiting real-time population data generated from cellular networks. We design effective features and D3DCN model to estimate the damage level based on our hypothesis. We validated our approach using two actual disaster damage data, and we found the experimental insights that the estimation performance can be significantly affected by the graph component direction and edge weight for DCN models. That's all. Thank you.